Okay, let's start our final topic, the final topic of this course, which is the Poisson process. Okay, the Poisson process has an incredible number of applications in engineering, especially networks and fields such as queuing theory. It's a very important discrete stochastic process. We'll study it as if it's a discrete stochastic process. It can also be viewed as a continuous stochastic process. Okay, so we defined our first stochastic process, meaning random process, last time. And that was the Bernoulli process. This is going to be another one and the last one in this course. Consider arrivals, okay? Such as buses, customers, photons, emails, etc. So whatever your context, we consider arrivals happening in time, okay? Occurring at random points in time. We say that the arrival process is a Poisson process if the times between arrivals are IID exponential random variables. Okay, so look at this figure. x1 is the time until the first arrival. x2 is the time from the first arrival to the next arrival. x3 is the time from the second to the third arrival. These xi's are called inter-arrival times. Okay? So precise definition of the Poisson process, one possible definition of the Poisson process is let x1, x2, x3, the sequence of inter-arrival times, be independent exponential random variables with a certain rate lambda. Then this process of arrivals is called a Poisson process. What is the mean time between two arrivals? 1 over lambda. Lambda is the rate of the exponential, so 1 over lambda is the expected duration of an inter-arrival time. Okay, example. I'm waiting for the bus, and bus arrivals are known to be a Poisson process, okay, at rate 1 bus per 10 minutes, say. Okay? Starting at time t equals 0, what is the expected time of the third bus? So, what is that? That is x1 plus x2 plus x3, right? That's the time of arrival of the third bus, because as seen in the figure, x1 plus x2 plus x3. So starting at time t equals 0, I wait for 3 inter-arrival times for the third bus. What is the expectation of that? Well, the xi's all have the same distribution, so this is 3 times the expected value of x1, which is 1 over lambda. What is lambda? Lambda in this case is 1 bus per 10 minutes. Okay, if you want, the units are buses per minute. Right? So this would give me 30 minutes. Any questions? Very simple. Inter-arrival times are exponential and IID. That gives me a Poisson process. But you'll see that it has a lot of nice and interesting properties. Any questions so far? Is everything clear up to this point? Yes, please. Right. So xi is exponential with rate lambda for all I. Okay. Great. Any other questions? Okay. Now let's see. Let's see some more properties of the Poisson random variable, or the Poisson process, sorry. Distribution of the residual time. Okay. I arrive at a random point at the bus stop. And the residual time is the time from this point up to the next arrival. Okay, so let's read from here. At an arbitrary time t, let r be the duration until the next arrival. This is called the residual time because it's only part of the interarrival time that t falls into. Okay? Now, let's sketch an example. So bus arrivals are occurring. Okay? And I show up at the bus stop at some time t. Okay? So I walk in. And then I'm waiting for the next bus, of course. This is not an interarrival time, right? Because an interarrival time is defined as the time between two arrivals. This is a residual time. Residual time, meaning the amount of time it will take on top of this time t for the next bus to arrive. What is most interesting about the Poisson process is that this residual time is also exponential with rate lambda, meaning the residual time distribution is identical to the interarrival time distribution. To understand this, we need to remember that the exponential distribution is memoryless, right? So let's, for example, okay, let's prove this. Okay, let's show that. Let's find the distribution of R. What is the probability that R is bigger than or equal to R? Okay, well, we can think about this interarrival time x that my t fell into. Okay? Now I can write R in terms of x, right?
But should we calculate R bigger than R, given that the interarrival time is x? In that case?
Well, okay. So first let's do the following. Okay. Suppose I arrived at some time t0 after the last arrival. Okay. Let's compute the following. Let's start with that. Okay. What is the probability that x, the whole time, is bigger than or equal to t0 plus r, given that x is already bigger than, let's lose the equal to, x is already bigger than t0. Okay? What are we saying? Given that it's already been t0 minutes since the last bus arrival, what is the probability that it will take at least r more minutes until the bus to arrive? We've essentially done this before when we worked with the exponential random variable. This is the probability that x is bigger than t0 plus r. Why? R is positive. So if you take the intersection of these two events, I get this event. Okay? Divided by the probability of x being bigger than t0. And that is, remember, it's e to the minus lambda t0 plus r because of the exponential CDF, complementary CDF, that is e to the minus lambda t0, which is e to the minus lambda r. So basically, given that I arrived at some time after the previous bus, the amount of residual time until the next bus is exponential at rate lambda. And this does not depend at all at how much time, on how much time has passed since the last bus. So irrespective of t0. Okay? So this tells me that the residual amount of time r is exponential at rate lambda. Okay, in general. So, this also implies that the Poisson process has the fresh start property. At every time, no matter what time it is, it's as if the Poisson process is starting from fresh, because the time until the next arrival is exponential at rate lambda. So just like the Bernoulli process, this process also has the fresh start property. Would you like that if you were waiting for the bus? Given that you waited 30 minutes, does not increase the chances that the bus will arrive any minute. Okay? So it doesn't matter how much you have waited. This is not a process that will be desirable for bus arrivals, right? And what would be desirable for bus arrivals? Do you think? We would all be happier if bus arrivals were deterministic, right? Right? Like every 10 minutes at fixed times. That would make life as plannable as possible, I guess. And also, it would minimize the variance of the amount of time you would have to wait. But we can talk about that later, okay? So, in fact, this exponential is an extreme case for randomness in arrivals because it has completely no memory. By looking at the past, you learn nothing about the future. If bus arrivals were deterministic at 10-minute intervals, for example, you arrive at the bus stop and somebody tells you that, okay, I've been waiting for 9 minutes. Then you know that the bus arrival is going to happen within 1 minute. Okay? But in the exponential, this tells you nothing in the Poisson process. Okay. So that's why it's maybe a difficult concept to get used to at first, but it's really fun, as we'll see. Okay. So on that note, given that I arrive at the bus stop at t equals 19 and learn that I have missed the second bus by 2 minutes, how much do I expect to wait? As a result of our discussion, it doesn't matter that the second bus left 2 minutes ago. The expected amount of time until the next bus is 10 minutes. Again, it follows from the memorylessness property of the exponential. Okay? Once this has sinked in, you will be able to move on to the other properties. Okay, any questions? Yes, please. Exactly, that's a very good question. This is the only continuous, well, let me first say this. The exponential random variable is the only continuous random variable with the memorylessness property. Okay? And therefore, the Poisson process is the only continuous time stochastic process with this fresh start property. Well, that starts fresh at any time. There's a more general class of processes called renewal processes that start fresh with every new arrival. Okay? But that's a more advanced topic. Okay? So anyway, by the way, what is the only memoryless discrete random variable? The geometric. Because think of the coin toss process. Every time I toss the coin, it's independent of previous time. So what is the number of times until the next head? It doesn't matter how many tails in a row that I got. Okay, the number of tails until the next head is still geometric. Right. Okay. Here's an equivalent definition of the Poisson process. An arrival process that satisfies the following two is a Poisson process. The probability pk comma tau that there are k arrivals in any time interval of size tau is given by lambda times tau to the k, e to the minus lambda times tau divided by k factorial. Do you recognize this? This is the Poisson PMF with mean lambda times tau. We need this, and we need the number of intervals in disjoint intervals to be independent. So this is an equivalent definition for the Poisson process. Let's try to illustrate this. So arrivals are happening at lambda arrivals per minute, okay, at a rate lambda. I take an interval of size tau. Okay. So the number of arrivals is going to be proportional to tau, right? I mean, the larger the tau, the more arrivals I expect to fall in to this interval, because the arrivals are coming in at rate lambda per minute. Okay? So the larger the interval, the more arrivals. In fact, the expected number of arrivals in tau units of time is exactly lambda times tau, directly proportional to the duration of time. And this makes a lot of sense. Okay. Now, our Poisson process satisfies that the number of arrivals is distributed according to a Poisson distribution with this mean. So the probability that there are k arrivals in tau units of time is given by lambda tau to the k e to the minus lambda tau divided by k factorial. Okay, k bigger than or equal to 0. So there may be 0 arrivals, right? Or 1 up to infinity. Right. Okay. In fact, this definition, this property follows from the definition of the process as exponential interarrivals. But this could have been used as an alternative definition. Okay, so provided that this is true and arrivals in disjoint intervals are independent, the resulting process is a Poisson process. Okay? It's really easy to see that this definition implies the previous definition. How do we see that? So this is an arrival, and this is the next arrival. And x is the time between these two arrivals. I want to find the probability that x is bigger than t. Okay, for example. Let's use this definition. The event that x is bigger than t is the event that t minutes pass and still the arrival has not occurred. Right? Inter-arrival time x is bigger than t if and only if there are no arrivals in t units of time. Right? X is bigger than or equal to or bigger than t if in the first t, so let's do this for example. If in the first t time units there are no arrivals, then the inter-arrival time x, let's mark it this way, the inter-arrival time x will be bigger than t. Okay? So what is the probability that there are no arrivals in t units of time? We'll use this with k equals 0. It's lambda t to the 0, e to the minus lambda t divided by 0 factorial. 0 factorial is 1, so we get e to the minus lambda t. What does this mean? This means that x is exponential with rate lambda. Okay. We all also know that arrivals in disjoint intervals are independent. So that implies that x1 and x2 and x3, all the sequence of inter-arrival times are mutually independent. So we get a Poisson process. So starting from this definition, we are able to get the original definition. If you're interested as exercise, you can show that starting from the original definition, you get this definition. And of course, it's done in the textbook, so you could refer to that. So, let's see. Let's do an example with this. How about, let's not erase this as yet. Let's read the example. I get email according to a Poisson process. Do you think the Poisson process is a good model for getting email? Why not? Well, it happens in distinct times, first of all, distinct points in time. And it's very unlikely that two emails arrive exactly in the same millisecond, for example, exactly at the same time, right? So at least it resembles a Poisson process this way. And well, memorylessness, I don't know whether it's a good model for everybody. But if you get email from various different sources, and they're all independent, it could be a good model that your incoming email process is a Poisson process. And this is related to an important approximation in network theory, the Klein-Rock independence approximation. But so far, let's stop questioning whether or not it's a good model and try to solve the example. So my emails are at rate lambda equals 0.1 arrivals per minute. Okay? If I check email every hour, what is the expected number of messages I find in my inbox when I check my email? So I check email every 60 minutes. Lambda is 0.1 messages per minute. And tau, my email checking period, is 60 minutes. So the expected number of emails that I get in tau units of time is lambda times tau. In this case, expected number of new messages is 60 times 0.1, which is 6 messages, right? Right. Next question is, what is the probability that I find no messages when I check my email? Just one message. And repeat this for an email checking period of 2 hours. Okay, so for example, if I check my email every hour and I don't find any messages most of the time, maybe I should increase my email checking period to 2 hours, right? Okay, so let's see. What is the probability of finding no messages? So in our notation, this corresponds to 0 arrivals in, maybe let's say k equals 0 arrivals in tau equals 60 minutes. Okay? It's lambda tau, which is 6 to the 0, e to the minus 6 over 0 factorial, which is e to the minus 6. Pretty low. So chances are I will get at least one email, right? This is, what is this? This is about 2 to the minus 2 times 10 to the minus 2 or even less. Okay, so let's find the probability that I get exactly one message. What is that? It's expectation raised to the power 1, e to the minus the expectation over 1 factorial. It's 6 times e to the minus 6. Much more appreciable probability, I guess. What is the probability that I get at least one message? 1 minus e to the minus 6. So should I be checking email every hour? I guess. So, because I will be finding, getting email, at least one email with very high probability. Okay. What about increasing the email checking period to 2 hours? How will my answers change? Let's do it here. If I make tau now 120 minutes, the expected number of new messages would rise to 12 messages, right? Because I've doubled the period. 120 times 0.1, which is 12 messages are expected. What is the probability that I get no messages? No messages, the probability of no messages reduces to e to the minus 12, which is, for all practical purposes, 0, right? What is the probability that I get at least one? This is exactly one. Exactly one has probability 12 times e to the minus 12 divided by 2 factorial. Oh, no, 1 factorial, which is 12 times e to the minus 12. The probability that I get at least one message is 1 minus e to the minus 12, which is approximately 1. Any questions? Okay, so now you know how to adjust your email checking frequency. If this is getting exactly one. Okay. In this case, the probability of at least one message is 1 minus e to the minus 6. In this case, that is 1 minus e to the minus 12. Okay, so it's increased, it's even closer to 1. Is this all fine? Is it clear? Okay. So let's continue. This is interesting. If you have a Poisson process, if you watch it backwards in time, it's again a Poisson process. We call this the time reversed process. So the time reversed process is also Poisson. What does this mean? Okay, we have arrivals. Inter-arrival times in the backward process, in the reversed process. So for example, the time from this point up to this point is an inter-arrival time in the reverse process. They have exactly the same distribution as the original process. They are exponential IID, okay, at rate lambda. Now what's interesting, and we will use this, the residual life process, the residual life R in the reverse process is again exponential at rate lambda. So I arrive at the bus stop at time t. What is the distribution of the time it has passed, the time that has passed since the last bus arrival? Exponential at rate lambda. Okay? Let's apply this. In the bus problem, what is the expected number of people on the bus that I get on? It's an interesting problem. Oops. Let's keep the problem. The number of people, expected number of people. Well, I haven't given you the arrival rate of people. I should give you that. Okay. So, first of all, let's compute. Forget about the number of people on the bus. Let's compute the inter-arrival time from the bus that arrived in the past before I came in to the next bus that I will get on. Okay? So I arrive at time t. Okay, I arrive. There was a bus before I came. This is the last bus. Arrival time of the last bus before I came. Okay? And this is the arrival time of the next bus. Okay? Now, because of the fresh start property, this time R1, let's say, R1, the residual time until the next bus, is exponential at rate lambda. But since the reverse process, going backwards in time, is also a Poisson process, this time R2 is also exponential at rate lambda. Why? Because the reverse process is also a Poisson process. Going backwards in time, there is the fresh start property, right? So it starts fresh at time t, going backwards. So this is an exponential time until the next arrival in the past. Okay? We can make these all technical, but I think for the scope of this class, we should not. Okay? So, okay. So let's compute the expected inter-arrival time that I sample by randomly arriving at the bus stop. Okay? Let's call this x. Expectation of x. What is that? It's the expectation of R1 plus the expectation of R2. That is 1 over lambda plus 1 over lambda, 2 over lambda. But an expected inter-arrival time was 1 over lambda. Let's plug in numbers. An expected inter-arrival time was 10 minutes. This is 20 minutes. What's happening? Am I just unlucky? What's happening here? This is sometimes called the random incidence paradox. It's not a paradox, but it looks like a paradox. Okay? When I arrive at random, the interval of time I arrive in has twice the expectation of a regular inter-arrival time. Why is this happening? Because when I arrive at random, I am more likely to arrive in a large inter-arrival time than a small inter-arrival time. Because there are more ways of arriving in a large inter-arrival time. There are more points in a large inter-arrival time than a small inter-arrival time. Okay? So if you remember, we saw this random incidence paradox again when we're talking about discrete random variables and averages. I asked you, for example, how do you find the average number of people on a bus? Okay. Do you interview bus drivers or do you interview people? If you interview bus drivers, that will give you the average number of people per bus from the perspective of a bus. Okay? Let me clarify this by an example. Suppose buses, so a given bus either has 100 people on it with probability 1/2 or 10 people on it with probability 1/2. Okay? So if you ask bus drivers, half of the bus drivers are driving a 100-person, very heavily loaded bus, and half the bus drivers are driving a very uncrowded bus. Okay? So the average, by asking bus drivers, is what? 55. Now suppose rather than that you interviewed the people, passengers. What do you get in this case? Well, I wish I chose numbers differently. How about I change this to 90? Huh? Then the average would be simply 50. Okay. Now, instead interview the passengers. Interview the passengers. Okay? 10% of the people will say, I was on a bus with only 10 passengers. Okay? They'll answer 10 people on the bus. 90% of the people, right, would answer, I was on a bus with 90 people. Why? So out of 100 people, 90 are in this bus, and 10 are on this bus. Right? Okay, so if you ask the people, the average will be computed as 10 times 0.1 plus 90 times 0.9, which gives us 82. Okay, right? So basically, the crowded buses are represented by more people. So if you pick people at random, if you pick a person at random, with 90% probability, that person is coming from this group. Right? But if you pick a bus at random, with 50% probability, it's coming from this group. Okay? Similarly, if you pick an interval at random, if you treat all the intervals equally and pick an interval at random, even the littlest intervals are being represented as much as the biggest intervals, right? But if you pick a time at random, you are more likely to fall into a big interval. That's why when you arrive at random, you see a bigger average inter-arrival time. Again, this is perhaps an undesirable arrival process for buses. Yes, please.
What if the buses did not have 1/2 chances of having 90 people or 10 people? If they didn't have equal chances?
You could compute that. Then the computation would be more involved than what I quickly did here.
So it has no effect on the passenger interviews?
Well, in general, interviewing bus drivers will be different from interviewing passengers. Only if buses were regularly loaded, the answers would be the same. Yes.
Hocam şimdi benim anlamadığım şey yani bence birinci hesabın daha doğru, ikinci hesabın doğru olmasının sebebi yani bana doğru gelmesinin sebebi oradaki 90 people'ın da hepsinin verdiği information esasında aynı. Bizim sadece bus'ın içindeki bir insana sorup ondan bilgi almamız gerekiyor. Yani o seçtiğimiz bir kişinin o bus'ın içinde yani bir bus'ın içinde olma olasılıklarını düşünmemiz gerekir.
But think about how much these people are suffering. So I mean, to be serious. Now, okay. So the governing body of the city, okay, city of Ankara, has to decide whether or not to provide more buses, more bus service. Okay, if they interview bus drivers, there seems to be no problem. Suppose the capacity of a bus is bigger than 50. On average, there are 50 people on a bus. That seems to be a no problem. However, do you think there's no problem? If the bus capacity is, 52, and there are sometimes 90 people on a bus, that is a problem, right? So the average experience by a person is saying that the buses is overloaded. So it's a change of perspective. Okay, they are both right according to their given perspectives. But if you care about the experience of a passenger, then this is a more correct average. Okay? But then again, averages are always, averages sometimes are misleading. Okay? So averages are first order statistics, and as I said before, I mean, they don't give us all the information about the distribution. Okay, so let's give a break at this point, and we'll continue with more properties.